Hello, so today we are going to consider the Millikan Oil Drop Experiment. We're going to consider the formulas associated with this experiment and some experimental procedures related to this experiment as well. And from that, we can deduce and actually understand why the sort of electron charge is known to be 1.6 times 10 to the minus 19 coulombs. And this is the electron charge. Well, this basically tells us that the electric charge is quantized, which basically means the sort of electric charge can only be whole number multiples of this value here. And let's sketch the experimental setup. So normally we will have parallel plates, and between the parallel plates we have just air, we have some sort of oil droplet, where the oil droplet we're going to consider in this experiment as negative. And in this case we will be expecting some positive plate on the top when we apply the potential difference later on. So basically these are all the things going on inside this experiment. So what we're going to do today is to consider each of these steps in order to deduce this quantity here. So first of all we are going to work out the radius of this oil drop, and then we are going to work out the mass of this oil drop. And finally we'll work out the charge of this oil drop, and from the value of the charge we can deduce this particular value here. So let's start with the first experiment. So in the Millikan Oil Drop Experiment, the first thing that we do for each of the oil drops that we consider, we first turn off the sort of potential difference, so we have zero potential difference between the plates. And in that sort of case what we have is some sort of free fall. So we have oil drop and free fall when we apply a zero potential difference between the plates. And we're going to consider its terminal speed. Well, we can actually conclude that an object is travelling at terminal speed when it takes the same amount of time to travel a same distance. So, same amount of time to travel the same distance. And what we can now do is to go back to the diagram here and consider some sort of free body diagram. So first of all we have something in free fall, something's falling, so of course the first thing that we can label is the weight, W equals to mg, the mass of the oil droplet multiplied by g. And in this case what we have is some sort of drag. So after all, the oil drop is moving through some sort of other fluid, which is the air, and of course with some sort of cross-sectional area and some sort of surface, then we have some sort of drag involved. And basically the drag, the expression for the drag is going to be given in your formula sheet. So the drag is equal to 6 pi RV. And this symbol is called eta. So basically what we have to do now is to quote Newton's laws. So first of all we are at terminal speed, and at the terminal speed the speed doesn't change. So if the speed doesn't change, something in constant speed or constant motion or being stationary, the force is being balanced. And that's why a drag here is basically balanced by the weight equals to mg. And basically by rearranging this expression we can show that we have an expression for the radius. So if I'll keep everything on the left the same, and I'm going to replace the mass of an oil drop with some sort of volume multiplied by the density. So the volume of this oil drop, we assume that this is a perfect sphere. So this is the ideal case. So in an ideal sphere we have 4 over 3 pi r cubed of volume, and we multiply that by the density, which is rho, and therefore we have this expression here. And what I have to do now is to basically rearrange this expression, make r the subject, where we have r squared on the left, and tidy up all the terms. I have 9 eta v over 2 rho g. And this is the first formula that you must know for Millikan oil drop. And in the exam you do not have to remember exactly what this formula is, but you should be able to derive it. And since we've basically worked out what r is by taking square root on both sides, we can actually work out what m is as well. And I can quickly write down that expression. So I can take square root on both sides. I can take just the positive root, because basically the radius is some sort of length. We are not going to consider negative values. So 9 rho v, eta v, 2 rho g, square rooted. We're taking just the positive root, and we can put it back into the expression for the mass. So mass of the oil drop is equal to m, and it's given by 4 over 3 pi r cubed multiplied by rho, so the volume multiplied by the density rho, and we'll have 4 over 3 pi 9 rho v eta v 2 rho g to cube rho. So that is the expression for the mass. So all we have to do now is to basically work out the charge. And to work out the charge, I'll have to consider applying potential difference across the parallel plates. Now, if I'll now apply some sort of electric field, of course, informed by applying some sort of potential difference between the plates, where I have my positive plate at the top and negative plate at the bottom. I have my negative oil drop, then of course naturally this will be attracted to the positive plate. So like charges repel, opposite charges attract. So let's say I have applied a potential difference that's just enough to keep the sort of oil droplet stationary. And with this setup, I can find the charge of this oil droplet. So the first thing, we have an applied potential difference across the parallel plates. And this applied potential difference is just enough to keep the oil droplet stationary. So basically the idea of holding the oil droplet stationary is important, because then we have to basically apply the formulas for the electrostatic force caused by the sort of attraction between the negative oil droplet and also the positive plate, and we must equate that to the weight. And in that sort of case, we must consider the stationary case, where the sort of forces are being balanced by each other. So what I have here is some sort of electrostatic attraction force, Fe, so electrostatic force, where basically the oil droplet still experience this sort of weight acting vertically downwards. I can now apply Newton's first law, where this sort of oil droplet is stationary, then Fe must be balanced by the weight. And Fe is basically some sort of electrostatic force, which is given by Q, the charge of the oil droplet, multiplied by the potential difference between the plates, divided by the distance between the plates, the plate separation. And that's equal to the weight, which means mg. And recall previously that we have obtained the expression for m, and we know what the applied potential difference is, which is this value here. We can measure the distance between the plates, and therefore we can rearrange for an expression of Q. So Q, the charge of this specific oil droplet, charge Q, is basically equal to mg multiplied by the plate separation divided by the potential difference across the plates. And therefore, we have obtained an expression for the charge of an oil droplet. And in the experiment, what we're going to do is to repeat these sort of calculations for more oil droplets, where we basically calculate the charge for each oil droplet each time. And the sort of charge that we obtain, the sort of value of the charge that we obtain, will always be a whole number multiple of 1.6 times 10 to the minus 19 coulombs, which is basically the charge of an electron. So basically the electron charge is given by the lowest common factor of the value of Q obtained from the experiment. And this value should be 1.6 times 10 to the minus 19 coulombs. So basically these are all the things that you must know in terms of a Millikan oil drop experiment. And that's the end of today's lesson. Well done.